Now you have the same beam. And let us say that yes, it is not at the center, it is at 2/3. Here. M naught is here now at 3L by 4, and this is L by 4. What? See, reaction, will there be any change in the reaction? Tell me. What will be the reaction? This is A and B. Now I have changed the position of the moment, applied moment. So reaction will be same. Will it change? Will it change to M naught by 3 and something like that? 3L by 2 it will be same. So it will be, reaction will be same. No change. Now here, what about shear force diagram? If you cut it over here, what will happen to shear force diagram? SFD. Will SFD change? See, now moment is acting here. SFD, what will be the SFD diagram? No change. Plus or minus. SFD. Next come to bending moment diagram. Yes, come here. Now this one up to here, bending moment if I draw, see my take M naught divided by L into X is the bending moment, like this. But any cross section, my bending moment will be what? This bending moment. Here I am talking of shear force, here I am talking of, let me say, a bending moment M. Up to here, it will vary linearly. X can be anything from 0 to 3L by 4. Up to 3L by 4, up to means less than 3L by 4. Not exactly up to 3L by 4, less than, so that M naught does not come, because at that particular point you have applied a concentrated moment. So my point has to be less than. So it will be bending moment. So this one bending moment, yes, this is a positive bending moment. So my bending moment will be, diagram will be, this will be 3 by 4 M naught plus, and the moment you will cross this M naught over here, there will be jump. Of course, this total moment has to be M naught. Out of that, 3 by 4 M naught is here. So at the bottom, how much it will come? And you can also see, you can also check that from the right hand free body diagram. You can also draw a free body diagram. Not necessarily you must take free body diagram from this end to this end. I can also take my free body diagram from this end. This end, this is from the right hand side I am drawing. And this is my X dash, just to distinguish between X and X dash. So I am saying I am measuring my X dash from the right B. From point B I am measuring. And my positive bending moment here is always like this, left or right. This is a negative X. This face is what? Negative face or positive face? Negative. Why it is negative face? Normal is in negative X direction. This is my positive X direction. Okay, but on a negative x phase also my bending moment is positive is like this. So what will be this? This is a negative because this m naught, this is m. So m plus m naught by L into x dash must be 0. Therefore, it is coming negative. This bending moment is negative here. Do you agree or not? This moment is, if you take, and it will also come negative from this side, which I have already shown you. So you can also take your free body diagram after a smaller one from the right hand side because it is simpler. Because I don't have to consider m naught here. My x dash will vary from here to here up to L by 4. So it will become how much? Negative. And then, so this one will be m naught by 4. Negative. So there will be a change in bending moment diagram, that is all. Nothing else. Okay? Reactions will remain the same. Now sometimes, so I am just giving you various possibilities. Now let us say next problem. Next problem. I have applied this is another problem, a new problem. So I have applied a moment at this end, at the support itself. No, at the support itself I have applied a moment, m naught. So you should be able to draw the deflected profile in the previous case of the beam. Now you tell me what will be the diagram here. Reactions will be same. So if you draw, again it will be m naught by L, m naught by L reaction, and moment is acting here. My m naught is acting here. Am I making any mistake? You draw the free body diagram and you go through the exercise of finding out reaction, you will find, yes, there is no other. My moment is acting there itself. So, then I wanted to tell you this. Yes, now shear force diagram up to here, up to the end. My shear force diagram again is constant, same positive. So there is no change in shear force diagram. This is m naught by L, positive. This is SFD. What about bending moment diagram? Bending moment diagram. Bending moment diagram at any cross section, x from the left end, there is nothing is coming, no force is there. So the nature will same. So bending moment here will be my positive bending moment here. M at any cross section will be m naught divided by L into x. M naught divided by L into x. Is it okay? Positive? Positive. And then it is true up to this end. So the same thing will continue. It will be a linear. And what is the variation? M naught divided by L into x. When x equal to L, it is equal to m naught. It has to be m naught because applied is m naught. So it cannot be more or less than that. At the point where it is applied m naught, you must have m naught. So here it is m naught. Because if you substitute x equal to L, you are getting. So my equation is this: at any x, it is m naught divided by L into x. Is it okay? So this is my BMD diagram. Positive. Positive? Yes. Positive? So no negative. So the bending moment diagram has changed. What will be the deflected profile? What will be the shape of the deflected profile if this is the axis of the beam? How this will deflect? Applying a bending moment. Like this. Tension at the top, compression at the bottom. See, this is what I have drawn. So this is a deflected profile. This is so there is no change, there is no point of contraflexion. There is no point change, there is no point of contraflexure here. In the previous case, there will be point of contraflexure, but there is no here, there is no, because this, see, the total tension is at the top. Point of contraflexure will come when tension from top, it becomes tension at the bottom. So, no point of, no contraflexure. So, next. So, this is all right. Supposing, of course, I should not waste time now, but I am just giving you next problem. Supposing the bending moment is applied over here, the m naught is applied at this end. What will be the change? What will be the change? What is the reaction? Same? Yes, I have not changed the direction of movement. But then there will be one difference that I want to show you is this. So reactions, let us say that this is going like this, so it has to be this is a reaction, so that this one will be opposing. This is a couple, this forms a couple here, m naught divided by L into L will give you L, m naught only. This multiplied by equal and opposite force separated by a distance L is nothing but a couple of magnitude m naught, whose direction is anti-clockwise, while the applied one is clockwise. So they are in equilibrium. So body is in equilibrium under the action of this. M naught is applied there. So what will be the shear force diagram? SFD diagram. Quickly tell me. SFD diagram, will there be any change? No change. So this is my plus m naught divided by L. This is SFD plus. What about bending moment diagram? What is that? What is it start? Yeah. Shear force you are talking, shear force or bending moment? Bending moment. Bending moment now will tell me. See, I can see bending moment will be bending moment. So this is yes. Positive or negative? At any cross section, positive or negative? Negative bending moment, right? write from the, it is negative bending moment, because I can also see, simplify from the left, from the right. If I take my free body diagram here and my positive bending moment is like this, so this plus this, if I take moment about this, so this will come negative. So negative, it is 0 here, and then it is, so this one will be m naught, and at any point, what will be the value? What will be this curve? What will be the equation of this line? When x equal to 0, it is equal to m naught, negative, but it has to be negative. So it is negative sign is there. Outside I have put negative, or it is x by L minus 1. It is x by L minus 1, I have put a negative sign outside, since I have taken. So when x equal to 0, it is minus m naught. When x equal to L, it is 0. So this one is negative. So you see, and what will be the deflected profile? How will the beam deflect? Bending moment is negative. It's drawn on the tension side. So it is. Will there be any point of inflection?
No.
By the way, point of contraflexure, and it is also called point of inflection. I think so. Just note it down. I'm not very sure, but I think it is point of inflection. Inflexion. Contraflexure means it changes its curvature. Now here you are applying a moment, so deflected profile will be like this. This is the deflected profile. This is BMD. It is, yes, tension at the bottom. So take it. Deflected profile. The deflected profile and bending moment, there is, one can see the relationship. It will deflect something like this. This angle and this angle will not be same. It is not that this is symmetrical. It is not symmetrical. This side deflection will be more. Left hand side deflection will be more. This side will be less. Is it okay? So this is okay. Same problem we can go to number of cases. 4. What is the date? Yes. Next problem. Not that I don't want to see further, but these are the things when we ask in the examination, you people mess up. There is m naught here, and I am also applying an m naught here. I can apply also m naught or m1 and m2. Two different moments also I can apply. I am putting it here same one. One is clockwise, one is anti-clockwise. Length is L. Now please find out the reaction. Tell me the reaction. Free body diagram. Reaction. Quickly, yes. Who will tell? Dhaka. Tell me the reaction. What is the vertical load applied on the beam? 0. What is the net moment applied to the beam? Anyway, you find out the reaction. You say, yes, take moment about this point. This moment 0 equal to L into this reaction. The reaction has to be 0. Take moment about this point. This reaction into this distance, net moment is 0. Applied moment is 0. So reaction has to be 0. So we also have a situation when reactions can be 0 and still beam will deflect and there will be a bending moment in the beam. It is not that always you must have, so this one, no reaction. So here 0 reaction, here 0, so this is 0, no reaction, this is 0. There is no reaction in this. Yes. What about shear force diagram? Yes, at any cross section here, shear force will be V. Is there any vertical force? Take free body diagram. Will there be any? No shear force. So SFT 0. 0 throughout. Throughout the beam, no shear force. No shear force. What about BMD? Yes, at any cross section, I want my PMD here, M. If I take moment about this point, this moment must be equal to my left hand side free body equal to M naught. So at any cross section, my moment remains M naught. Because there is no reaction, so V into this reaction into distance will not come in the picture. Normally what is happening in the other case, because there was a reaction, so this into this distance was coming in the picture. Now here it will not come in the picture. Okay, so it is M naught. So throughout my bending moment is M naught only, not 2M naught. Positive, tensile. Now this beam, yes, there is a difference in the deflected profile of this beam. So this is deflection. Yes, what is the difference between this deflection? Earlier the axis was horizontal and now after M naught have been applied. What will be the shape of the deflection? It will be symmetric. Yes, this is the difference. M naught will produce symmetric. So this deflected profile will be symmetric. It is symmetric. It has to be symmetric. And it has to be like this. So one can complicate and this now you can if you have a next problem, not that I want to only do this problem, but if you have now you apply M1 and M2. At the two ends, what will happen? Draw the free body diagram, find out the reaction. Length is L. Same problem. Yes, what is the reaction here? Now I have to say which one is bigger, which one is smaller. Let us say M1 is more than, otherwise you cannot solve this. I have to say that yes, M1 is more than M2. Moment M1 is more than M2. So please find out the reaction. Quickly. Yes, how much is the reaction? Huh? Is it okay or? Up and down. Is it okay? Yes. Reactions will be like this, up and down. And you should also visualize now. This is more. So applied moment is like this. This side is more. So my reaction has to be like this. So it has to be downwards here, upward here. This has to go through all the three steps of finding out, writing the three equations of equilibrium, and then finding out reaction. Once you have found out, then now problem is you can now draw the bending moment, shear force diagram, etc. etc. Yes, please. I will. This is my last problem as far as this example. I mean, this symmetry is concerned. Yes, shear force diagram. Yes. How will be shear force diagram? Into x. X कहाँ से आ गया भाई? Shear force diagram I am saying. This is the horizontal axis. So what is the shear force diagram? At any cross section here, my shear force is like this. Positive shear force I have shown upwards. So this plus this, so this one will be equal to negative of this. And that will continue throughout. So it is a negative. This is negative. By L. We are negative. Yes. Which one is axis? No. This is so negative means it is coming down. This is axis. See, we always have. So it is. This one will be equal to yes. This is my shear force diagram. This is the axis and negative. This one is down. Is it okay? Bending moment diagram. At any cross section, I will take another cross section here. My positive bending moment is like this. On the left, on the positive x face, my positive bending moment is like this. So this is this plus, so this direction and this direction is same. So this one will be negative of this. So that means this bending moment will be negative. This m2 minus m1 by L into x. Negative. I mean negative means it is m2 minus m1. Is it okay? Or m1 minus m2 by L negative into x negative. So and then up to which point? Shear force is okay. And bending moment. यहाँ negative हो गया. Then it can how it is coming? But at this point, it has to be zero now bending moment. No, it has to be M1. It has to be M1. So, कैसे होगा? Because bending moment ये भी है. This into this and M1 भी applied है ना भाई. M1 तो है ही है यहाँ पर. This one, M2 is they are there. So total bending moment here will be this into this minus M1. I mean, this is equal to this minus M1. Yes. See, at any cross section bending moment, I will just draw, I will write it. Silence please. At any cross section, if you take this cross section, I am trying this bending moment. This into x. So it will be m1 minus m2 by L. This bending moment is positive as far as into x minus m.
Minus of this. Minus of this.
Oh, this one is minus. This is plus and this is minus. Yeah. This is plus and this is minus because this is positive. So this one is yes. Is it okay? So does it when x equal to 0 it is m1. Now when it will become 0, that means somewhere it will become 0. No? When x equal to n, when x equal to n, how much it become? M2. And in between? No. So here it is m1. Yes. Here it is m2.
M1 is greater than M2.
M1 is greater than M2. Okay. So larger. And M2 I'll make it shorter. So it is and what? So this is M2, this is M1, this is BMD. There it was a constant. When M0 were applied, we had a constant bending moment. Here it is inclined line. Is it okay? Shear force you have seen. So shear force there is no change. Bending moment, yes. So you have seen by various changes what can be. Now let us take 6. Supposing you have I hope you have not repeating. What's that? Deflection profile for this one will be similar. Deflection profile except that, yes, deflection profile, it will not be symmetrical, so it will be less on this side. It will be like this. This is deflection. Non-symmetrical. So this side is, because this side is bending, so it will, and then this side. Alright, so next one. Now let us say that I have this problem. I have a bending moment, a simply supported beam. I am not changing. I will change after this problem. At 1/4 I have a bending M0. M0 applied at L/4. Then at this point, at 30 degrees, I am having a load P at the center at L/2. And then again L/4 here, I am having distributed load. So there are 3. Yes, now this is the problem. So this is L/4. And this again is L/4. Yes, please. And this is L/2. How will you solve it? On the same beam A, B, You have 3. Now this load is per unit length. This is distributed load. Uniformly distributed load. It can also be variable, but here I have given you. So let us say it is P naught. Small P naught per unit length. Per unit length. Okay. So this is now. How will you solve? One way is to solve as it is. Find out the reaction. Find out the support reaction. Three reactions. You can find out. You will be able to find out. Free body diagram and then 3 reactions. Because of this, there will be M naught by L reaction, plus or minus. That you can see. This can be split up into vertical and a horizontal force. Central one can be P cosine 30 and P sin 30, and this one will give you an equivalent load of P naught L by 4 upwards and applied at L by 8 central. Resultant force. Resultant of this. Now you can find out based upon this. So now next problem is, yes, see, these are the ways you must look at when the problem is complex. So you think, okay, this is my reaction here, HA, VA, this one is VB, this one L by 4. What will be the total load here? P naught L by 4. This total load is upwards. P naught L by 4 applied at center of gravity of that, and that is P naught L by 4 applied at a distance L by 8. This is L by 8. Is it okay? Centroid. Is it alright or not? This total load, this is UDL. This is a UDL, uniformly distributed load. Intensity of load is P naught. So total load is P naught into length. What is length? L by 4. So L by 4. Total load upwards, and that will act as a center. Center is at what distance? L by 8. Now this one at the center here is how much? What is this component, please? P sin 30. P sin 30 is how much? P by 2. P sin 30. P by 2. P by 2. And what is P cosine 30? P cosine 30 root 3 by 2. P into root 3 by 2. So one is horizontal at that point, and this is M naught. So yes, I can find out the reactions. I can take equilibrium and then find out. There are 3 unknowns. You should be able to find out the reaction. And please draw. Now you will note here that there will also be axial force here, because there is an axial force here applied. Yes. But can you tell me quickly, one person who will tell in the end, even without finding out the reactions? Can we draw the axial force diagram? Yes. Okay. So what is the axial force diagram? This is the axis I want to draw. Yes. Come on, quickly. P by 2. Axial force diagram. Root 3 by 2. Plus or minus. Axial force diagram. AFD. Yes, tell me. Plus, what will be the value of HA? HA will be equal to P root 3 by 2. So, plus or minus. at any cross section, if this is the length, when you are doing axial force, so at this end you have HA. HA is equal to P root 3 by 2. So at any cross section, what will be this? What is the notation that we are using for axial force? No, just like B we are using bending moment and N. Yes. So this is Nx, positive Nx. So this plus this equal to 0 or Nx equal to minus. So what is the meaning of minus? Physical meaning of minus. Compression. What compression? Where compression? That means from here to here, this half of the beam will be under compression. What about the remaining half? It will be under tension. Sure. 100%. Roller is here. If you give this reply, 0. From here to here, no force. From here to here, no axial force. Only this portion is subjected to an axial compression of equal to P root 3 by 2. And that diagram will be like this. Negative, minus P root 3 by 2. This is AFT. So I just wanted to, other things you can do. See, we have already done for central point load. I have already done for M naught. Again, because of this is also a concentrated load, you should be able to find out. Now, please find out the values of all this VA, VB. Okay, and then draw the bending moment, shear force, axial force diagram. But then I will suggest that this problem can be thought. I will just take. So the original problem is also equivalent to this problem total. Total problem, which is M naught, and here it is this is equivalent to this three vertical line means equivalent to 3 or 4 problems. I can tell you this is equivalent to a single problem. So always think in simply, in simple terms. Don't complicate your thinking, because then you will make mistake. This is equivalent to a single force plus another problem, because total load applied on the system remaining the same, another force plus another force moment here, M naught, plus what? What is left? This one. So I have divided this AB problem, one problem into 4 problems. 1, 2, 3 and 4. So this is combination of 1 plus 2 plus 3 and plus 4. Try to solve these 4 problems separately. And you have a standard, because then you cannot make mistake. See, total load applied on the system is equivalent to this. So, and draw the axial force, bending moment, shear force diagram for each individually. Get it or not? Are you following? Each 1, 2, 3, 4 separately, and then superpose. Superpose means add one over the other. Is it? You get it? So please solve this problem like this also. So always think in, your thinking should be simple, not complicated. Don't always think in complicated. Oh, they are so complicated. So many forces are there. So how to do? And you will start shivering. Don't shiver. Simplify it. Yes, this can be split up into so many, because total load remaining the same on the system, we are still, the sum of all these individual solution will be equivalent to solution of this total problem. Is it okay? This is called superposition, principle of superposition. Only thing is, this principle of superposition, you can add everything, bending moment, shear force, deflection, anything is applicable only under certain conditions. What are the certain conditions? I think I told you right in the beginning, first class. Linear response. Material must follow stress strain curve must be linear under this. Not that it exceeds total here, it is exceeding beyond yield point. No. Straight line. Then deflections are small. We are tracking of micro deflection. 1 millimeter, half millimeter deflection of a rod of 1 meter. So we are talking of very, very small deflection. The moment it becomes large, you will have to take, we cannot do this summation. So one is, so first part is called, deflections are small, we say geometrical linear problem. It involves geometrical non-linearity. Geometry should not change. My deflections are such that I can take my equilibrium in the undeformed state. Otherwise, I will have to consider the equilibrium in the deformed beam. So they are so small that I am considering only straight line, horizontal line, not deflected profile. So that is called geometrical assumption, geometrical non-linearity. So we are not considering geometrical non-linearity, we are considering geometrical linear. And second one is material follow, material is a linear material. Material follow, my Hooke's law is linear. So these are very, very important. So I think we are considering that equal to 100%. So we stop here and I will take attendance.